Alrighty, good morning everybody. Welcome back to Math 105. Plan for today is we are going to continue our discussion of implications, if-then statements, and potentially finish. I'm not quite sure if we're going to get through the rest of the packet today, but I hope to. On Monday, I've got my usual Monday morning office hour from 10 to 10:50, but just so you know, I will not have my Monday afternoon office hour because I have another engagement I have to sit in on another professor's class. That's time. As far as homework goes, homework kind of depends on how far we get today. If we finish standard 4, then I'll post a quiz over the weekend. And if we don't, then I won't. And I'll post it on Monday, after Monday's class instead. Any questions or comments before we get going for today?
What's the joke?
Where do they put mathematicians who commit crimes?
In a prism?
In a prism! It's so that they can be with all the other convicts. Okay, so when we last left off on Wednesday, we had started talking about Standard 4, which is all about implications, if-then statements. And we said the way you kind of denote if P then Q symbolically is to write out P, arrow pointing to the right Q. And you read that off as if P then Q. And we said that if P then Q means that in every circumstance that P is true, Q also has to be true. Meaning the Venn diagram for your P and Q has to look something like this, where all the circumstances under which P is true would also be circumstances under which Q is true. But you could certainly have that. You could also certainly have that Q is true without P being true, or that neither P nor Q are true. The only situation that if P then Q is prohibiting is the situation where P is true and Q is false. So that's where we left off on Wednesday. We kind of talked about some examples of how can you write this symbolically in words, what do these implications mean. Today, I'm going to start off on the page of the packet that says, note that some statements can be written as if-then, even if they do not appear in that form. So today, I'm going to start off by talking about ninja implications. And by ninja implication, I mean statements that can be written as implications, even if they don't necessarily look like it. It might be worded slightly differently, but are still nonetheless implications deep down. So, start off with this one. Whenever it rains, I bring my umbrella. I claim this is an implication, despite the fact that it does not have either of the words if and then in it. No ifs, no thens. Nonetheless, I claim this is an implication. How could we write this? How could we reword this sentence so that it means the same thing, except that it also includes the words if and then, and so it kind of looks like in the form of the implications we were studying on Wednesday.
If it rains, then I bring my umbrella.
If it rains, then I bring my umbrella. I agree. Where here, the word whenever is kind of taking the place of both if and then. Whenever it rains, I bring my umbrella. If it rains, then I bring my umbrella. What this is really saying is that under every circumstance where it rains, it has to be the case that I'm bringing my umbrella. So as a quick review, so if this implication is true, let's say this implication is true and it's not raining. Can I still bring my umbrella? Can I leave my umbrella behind? Yeah, exactly. It turns out that if this implication is true, and it doesn't rain, then this implication makes no claims as to whether or not I bring my umbrella. So if it doesn't rain, I can bring my umbrella, or I may not bring my umbrella. Either way, those would be situations that would make this implication true. The only way that this implication could be made false was if it were to rain and I were to not bring my umbrella. How about the next one? I do not eat meat on Sundays. Actually, here's what I should be doing.
If it is a Sunday, I do not, then I don't eat meat.
If it is Sunday, then I do not eat meat. I like it. I like how you kind of reverse the ordering of the things in the sentence. You kind of move Sunday to the front of the statement and made it part of the first statement. And you kind of took something that only really had a single verb, do not eat meat, and you kind of constructed another statement out of just it being Sunday. I like it. If it is Sunday, then I do not eat meat. What does this double arrow mean?
It means the two statements are logically equivalent.
Bingo. Means they're logically equivalent. Mathematically, they're the same, even if they're worded a little bit differently. So if either one of these is true, the other has to be true. If either one is false, the other one has to be false. Here's a relatively simple statement that has a quantifier to it. All kangaroos.
If it is a kangaroo, then it hops.
If it is a kangaroo, then it hops. So here, kind of coming up with this new pronoun it that wasn't anywhere in the original statement, where it here is, I assume, I don't know, what could it refer to?
The kangaroo, sorry, the subject.
It could refer to a kangaroo, does it have to?
I mean, if the sentence is true, then it is a kangaroo. But if it is not true, then it's not a kangaroo.
Well, considering this is an implication, I don't think that our original statement, let's write this out with P and Q. I don't think our statement P has to necessarily be true in order for the whole statement to be true. I think it's very much possible that this implication holds true, and yet you still were talking about something that's not a kangaroo. Maybe you're talking about this chair. And we can look at this chair, we can study it from different angles, we can say, if this is a kangaroo, then it hops. Doesn't seem to be hopping. It's probably not a kangaroo. Point is, there's this sort of it that's involved in, it kind of depends on the context what it could refer to in this sort of scenario. It could refer to any number of things, I would say. And even if we're applying this to something like an inanimate object, we could still have this implication could still be true if the first statement P turns out to be false. If the first statement is false and the second statement is true, the implication can still be true. No pigs can fly.
If it's a pig, then it can't fly.
If it's a pig, then it can't fly. I like it. This mysterious it is appearing again. This kind of it has in the last one, but I like it. If it's a pig, then it can't fly. So this one's in. I thought this one was interesting because it uses a quantifier of no pigs fly, and yet you're still making a statement about something that pigs can or can't, that pigs can do. And we could just say no pigs can fly is logically equivalent to if it's a pig, then it can't fly. Just negate the verb in the second half in order to kind of make that implication be logically equivalent to the original one. And finally, x equals 4 implies x squared plus 1 equals 17.
If x equals 4, then x squared plus 1 equals 17.
If x equals 4, then x squared plus 1 equals 17. Is this a true statement? What if I wrote it the other way around and said, if x squared plus 1 equals 17, then x equals 4? Well, in that scenario, I would say if x is allowed to be negative, then that could be false, because you could also have x equals negative 4. That would make this one true and that one false. Point is, though, lots of different ways to sort of write these different types of implications in ways that do not necessarily use the words if and then, but a lot of statements that aren't written that way can be logically equivalent to statements that do have this if p then q structure.
I was going to say that you feel as though there are going to be no numbers.
I think
You might have.
Did I told you there's not going to be like any number crunching. And I may have what? There might be a minimal amount of number crunching. I'll sneak it in when I can, and if you all start complaining, then I'll add more.
If x was negative 4, wouldn't it still be 17, which is negative because it's squared?
Bingo. That's what I said. Like this one would be true. Because if x is 4, if this one is true, then this one has to be true.
Oh, I see what you're saying. Yeah,
But
it
but
could be
it's
4 or negative.
using a word that we're going to introduce later in this class. The converse of this statement would be false. It would be false to say if x squared plus 1 is 17, then x equals 4.
Okay. Is there a way to like account for like 2 in if then statement like for 2 possibilities? Could you say like if x squared plus 1 equals 17, then x equals 4 or x equals negative 4?
That would be a way you could do it. Let's write that one down. If x squared plus 1 equals 17, then x equals 4 or x equals negative 4? Sure. That would sort of be a statement of the form if p, then q or r would sort of be the format of that. And I would say this one has to be true. In any circumstance where this is true, this would be our p, at least one of these two individual statements has to be true. Oh, in this case, exactly one, because both can't be true at the same time. But sure, you could totally phrase something like that. And now this, I agree, would be a true statement. Implies is kind of a common way to, where did I put implies? Imply, to write an if-then statement. If P, then Q. We'll very commonly see later in this course that being written in the form P implies Q. And here, P implies Q just means the same scenario of if P, then Q. Every circumstance under which P is true, Q must also be true, if the implication is true. Any questions or comments about these phantom implications? Okay, so next up, I want to talk a little bit about how you can negate an implication. Negating an implication is kind of interesting because it's a little bit counterintuitive to me. When we negate an and statement, we needed an or statement back in standard 3. When we negated an or statement, we wrote the negation in the form of an and statement. When we negate an implication, it's also in the form of an and statement. So let's write this down. So it turns out that the negation of P implies Q, or if P then Q, can be written in the form P and not Q. Why is that? Why is it that the negation of an implication, if P then Q, turns out to actually be this and statement instead?
Because when P is true and Q is not, is the only time that we can definitively say the implication is not true.
Exactly. The only scenario under which if P then Q is false was that scenario number 2, where we won the tennis match, but we didn't get ice cream. The first statement came true, and the second statement didn't come true. And so the way you would negate this implication, if you win, then you get ice cream, was to be in scenario number 2, the scenario where you win and you don't get ice cream. P happens, P is true, but Q is false. So I would write this down as saying, why is this? Because P implies Q is true in every situation except when P is true and Q is false. And therefore, the only time that its negation should be true is in that scenario, when P is true and Q is false. So this is the only scenario when its negation is true. It's the scenario where P is true and Q is false. Or in other words, the scenario where P and the negation of Q is a true statement. So here, just writing this out using this logical equivalence term, we can say that the negation of P implies Q, the negation of if P then Q, is logically equivalent to just saying P is true, Q is false. Any questions or comments about that? In that case, I want you all to take a few minutes and try negating the implications on the next page and a half of this packet. Starting with if it is hot outside, then I don't wear a jacket, and going on to the bottom of the next page. We'll come back together in a few minutes and talk about a few of these. As always, if you feel comfortable doing so, you can talk to your neighbor about it and see if they agree.
Oh, for down here. Well, there are two. That's it, yes. We'll see. I'm not quite sure.
Alrighty, let's come back together and talk about 4 of these I've picked out. If it is hot outside, then I do not wear a jacket. How can we negate this one?
If it is hot outside, then I do wear a jacket.
So your negation of if P then Q is if P then not Q. What do you all think? Seeing a little bit of disagreement.
It is hot out and I'm wearing a jacket. On the accident.
Yeah. Counterintuitively, the negation of this implication is not actually going to be another implication. I would say, let's see, if this is going to be our statement P, and this is our statement Q, P is if it is hot outside, statement Q is I don't wear a jacket, then our negation is going to have to be of the form P and not Q. So in other words, it is hot outside, and I don't wear a jacket.
Yeah, I do wear a jacket.
And I do wear a jacket. I forgot to negate. It was already good. Good catch. So here, our negation is going to be P and negation of Q. P, it is hot outside, and negation of Q, I do wear a jacket. How about this next one? The mice play if the cat is away.
Cat is away and the mice are not playing.
The cat is away and the mice do not play. I like it. This one's a little bit deceptive because I wrote it in the opposite order. Technically, this is logically equivalent to saying if the cat is away, then the mice play. So that our P statement is actually the cat is away, and our Q statement is actually the mice play. Even though I wrote this statement in a way that made it in which the Q actually appeared before the P. It's because the P is not necessarily whatever comes first in the statement, it's the part that's following the if. And so the negation would be P and not Q, or in other words, the cat is away, and the mice do not play. Questions or comments about this one? This one's a little bit trickier. Okay, here's one where I just gave you something symbolically. P implies Q and R.
P and Q or negation of, or sorry, yeah, P and negation of Q, negation or negation of R.
Ooh, you're skipping straight to the simplified version. Yeah, that's absolutely right. I would have done this in a couple different steps. And first I said P and negation of Q and R. We're just saying the first statement and negation of the second, where the second is going to be this compound statement, Q and R. And to negate P, it implies compound statement. We need P and negation of compound statement. And how did you negate Q and R?
By making an or statement and negating both Q and R.
Yeah, so it becomes not Q or not R. So either one of these I think would be correct. P and negation of Q and R, which as we saw back in standard 3, the negation of Q and R is going to turn out to be, is logically equivalent to not Q or not R. Negation of Q and R both have to be true is at least one of Q and R is not true, which we get from swapping out our Q's with not Q's, our R's with not R's, and our and with an or. And finally, Q implies R and not P implies not Q. This one is a bit of a mouthful.
I had, so in parentheses, Q and not R, close parentheses, or a new set of parentheses, the negation of P and Q.
Like that?
Yeah.
Seeing some strange faces though around the classroom.
Why wouldn't you just say and? No.
Yeah, where did this or come from?
Don't you switch and or when you negate the statement?
I think she's right. If you are negating, the original statement was an and statement, and we're negating the whole thing. So if you've got two separate implications on either side of an and statement, then in order to negate the whole statement, you have to switch that to.
I agree. I think one way that helps.
But we don't just switch the and to an or, we also have to negate the quantity.
Yes, yeah.
So here, the way that's helpful for me to think about this is to take kind of these implications and just write them as new statements. Let's call this one A and this one B. Then the statement we're actually trying to negate ends up just being a statement of the form A and B. Because we have implication A and implication B. How do we negate a statement of the form A and B?
Negation of A or negation of B.
Yeah, the negation of this is going to become negation of A or negation of B. And I think that's exactly what we did here. This will be the negation of our A statement, where A said Q implies R. Negation of that is going to be Q and not R. Or negation of B. If B was of the form not P implies not Q, then the negation of that would be not P and Q. So this was kind of a lot for me to try to do all at once. I struggled with this one. But I found it pretty helpful to just say, all right, instead of trying to do everything all at once, let's make this a little bit simpler and call this implication A, this implication B. Because to me, negating a statement of the form A and B is a lot easier than trying to negate Q implies R and not P implies not Q all in one go. Because negating A and B, that's a standard 3 question. That's something we've talked about. It just becomes not A or not B. And so then, if we want to write out not A or not B, we can then just negate A and B individually by using our knowledge of how we negate an implication. Where we negate Q implies R by just saying Q and not R. We negate not P implies not Q by just taking first, which is not P, and negation of Q, which is just going to be logically equivalent to Q again. So by breaking it up into kind of steps like this, I think it becomes a lot less daunting than trying to do it all in a single go. Any questions or comments about this one? Getting some of these, especially these more complicated ones, I think is something that takes some getting used to. So I definitely encourage you to make sure you've had a good look at the other negation statements, implication negations. That's what I'm saying, implication negations in this passage. So the last thing I want to talk about for today is, given an implication P implies Q, if P then Q, we have three associated implications that kind of share a special relationship with P implies Q. And that is the idea of taking the converse of an implication, the inverse of an implication, and the contrapositive of an implication. Where if your implication is originally of the form P implies Q, if P then Q, the converse to that implication is going to be of the form Q implies P. The inverse, this is going to be the converse of P implies Q. The inverse of P implies Q is going to be not P implies not Q. And finally, the contrapositive of that implication of P implies Q is going to be not Q implies not P. Where all of these are going to be implications, and given the original implication, P implies Q, you can find the other three implications, the converse, the inverse, the contrapositive, by just swapping the order of the P and the Q potentially, and possibly negating the P and the Q statements. So let's do an example. If the pig has wings, then it can fly. So this is going to be our original implication, kind of the original if-then statement. Where we have a statement P, which is the pig has wings. We have a statement Q, it can fly. And our implication is of the form if P, then Q. Kind of the way we're used to working with implications. How could we write out the converse of this implication? The original statement is P implies Q. And what would the converse look like? Q implies P.
If it can fly, then the pig has wings.
If it can fly, then the pig has wings. I'm going to rephrase slightly to just say if the pig can fly, then it has wings. Just to make clear that the thing that we know to be the subject, the pig, comes at the beginning of the sentence. Just avoids a little bit of ambiguity early on. But if the pig can fly, then it has wings. I like it. Q implies P. How about the inverse?
If the pig does not have wings, then it cannot fly.
Not P implies not Q. If the pig doesn't have wings, then it can't fly. And finally, how about the contrapositive, the original implication? Not Q implies not P.
If the pig cannot fly, then it does not have wings.
If the pig can't fly, then it doesn't have wings. Absolutely. All of these are very similar sounding statements, where they all involve pigs having wings or not, and they all involve pigs being able to fly or not. They're all basically they're all implications that involve P and Q, but the four different ways of taking an original implication and swapping the order of the P and the Q, the original but negating the P and the Q, and the original where we've negated the P and the Q and we've swapped the order. So there's several more statements here I encourage you to try with. And here is going to be my challenge for you for the next several minutes. Given an implication of the form P implies Q, one of these three statements is going to be logically equivalent to the original one. Your job is to find out which one. And to do that, here's going to be my challenge to you. I want you to try negating each of these four. So here I'm on the last page of the packet. I want you to try negating each of these four statements and see which one of these three has a negation that's logically equivalent to the original statement. So the original, the implication, is P implies Q. Converse, Q implies P. The inverse, not P implies not Q. And the contrapositive is not Q implies not P. So try negating each of these four and see if you can find which one has a negation that's equivalent to the negation for the original implication, P and not Q. And whichever one has the same negation as the implication will also have been logically equivalent to begin with to the implication. Take a minute and think about that. So, running a little out of time, so sorry I need to cut you off here. If the negation of the implication P implies Q is P and not Q, P in negation of Q, how can we negate the converse, Q implies P? The negation of the converse ends up looking like
Q and not P.
Q and not P. First and not second. I like it. So Q implies P gets negated to Q and not P. Are these two logically equivalent to each other? Doesn't really look like it. This kind of looks like they're negations of each other, in fact. Huh. How about the inverse? Not P implies not Q. What happens if we try to negate that one?
Not P and Q.
Not P and not Q, which is the same as saying not P and Q. Was that negation logically equivalent to the original one? Is this logically equivalent to anything else?
Yeah.
Which one?
The converse.
Yeah, it's going to turn out these are logically equivalent, which will tell us these are also going to be logically equivalent. Yeah, six. Finally, we have the contrapositive, not Q implies not P. How can we negate that one?
Not Q and P.
Not Q and not P, which is P. Is that one logically equivalent to the original negation? Yeah, these are kind of the same. P and not Q and P. The order of the two statements in an and statement doesn't matter. So these are actually going to be logically equivalent to each other. And so we can say, in general, the original implication, no matter what it says, is always going to be logically equivalent to its contrapositive. Which is kind of ironic, if you ask me, because it looks like out of the converse, inverse, and contrapositive, the contrapositive is the one that looks the least like the original implication. And then to get from the implication to its contrapositive, we not only have to swap the P and the Q, but we also have to negate the P and the Q. Sort of like a double negative canceling each other out, swapping the P and the Q, and taking the negation system. Turns out if you swap the P and the Q, and if you negate the P and the Q, you get something that's logically equivalent to what you started with. And similarly, the inverse and the converse will also be logically equivalent. Let's look at a quick example here. If the original statement is, if you win, then you get ice cream. The contrapositive, this is going to be our original implication. What would the contrapositive be to this statement? Where here the P is you win, and the Q is you get ice cream.
You don't win, then if you don't get ice cream, then you didn't win.
If you don't get ice cream, then you didn't win. I like it. It's going to be not Q. So if you don't get ice cream, then you didn't win. The not P. I claim these are logically equivalent because this one says in every scenario where you win, you must get ice cream. It's impossible to have you winning but not getting ice cream. Whereas this one is saying if you don't get ice cream, then I guess you didn't win. Basically saying, well, if P happening requires that Q also happens, if Q didn't happen, I guess P couldn't have happened either. Because if Q didn't happen and P did happen, that's the situation that would break this implication as well as this one. Yes?
Couldn't you get ice cream without winning?
Can you get ice cream without winning? So that would be a Q and not P? I think Q and not P is totally okay. So that would be like the scenario number 3 that we from the ice cream winning scenario where we talked about. And that's something that would be a situation where you didn't win, but you still got ice cream. That would make both the implication and its contrapositive true.
I guess my question is that in the original implication, you're able to get ice cream without winning.
Yes.
But in the contrapositive, it seems like you're not able to get ice cream unless you win.
Well, if you don't get ice cream, then you didn't win. Remember that if the first statement in an implication, or in this case in the contrapositive, is false, then the implication here, I keep using the word implication. If the first statement in the contrapositive is false, then just like in the original implication, the contrapositive has to automatically be true. This is making a claim about if you don't, I'm making a promise that if you don't get ice cream, something has to happen, that you didn't win. But if you do get ice cream, then it doesn't matter. Then it doesn't matter if you win or didn't win. My promise to you is fulfilled either way.
Okay.
So one last thing, and here's kind of the kicker to this whole discussion. If P implies Q and Q implies P are both true, then we can say something special about the relationship between P and Q.
Are they logically equivalent?
They're logically equivalent. And this is sort of, I think, suggested a little bit by the notation in that if we have an arrow pointing to the right from P to Q, and we have an arrow pointing from Q to P, it's like we have a double arrow pointing back and forth between P and Q. And so that's why we actually use this symbol for P is logically equivalent to Q as the double arrow, because that really just means if P then Q, and if Q then Q. It's going to do it for Standard 4. When we come back on Monday, we're going to start Standard 5 and talk about how to construct truth tables. I hope you all have a good weekend. I will see you all on Monday.